Hello and welcome to lesson 7.5, the cross product of two vectors. Today we're going to examine another product called the cross product, or sometimes also called the vector product. The cross product of two vectors is to find a vector that is orthogonal to both of the original vectors. What you're going to notice is this result is proven in a supplementary document called the proof of the product of the two vectors, and you can check that out if you'd like. Please realize that the cross product can only be applied to vectors that are three-dimensional. Cannot be applied to any other vectors of any other type. So, if you wanted to find a cross product between two vectors, let's call it A, B, and C, with D, E, and F, then this is the formula you'd have to memorize. As you might notice, this formula is a little challenging to remember or recall, and therefore a short form, or a different way to remember it, is shown below using the matrix. So what we use are our titles of I, J, and K, and then repeat it. Then you take your first vector, A, B, and C, and you list them like so. Then you do the same thing with D and F. So to remember this, you start on I, and you go diagonally across to B and F. Oops, slightly missed. Let me redraw that. So then you start out by writing B times F, whatever you crossed, and then you start on the other I and you go diagonally across the other direction and subtract CE. That'll be your first one. That'll be your first component. Do the same thing with J. So J crosses D and E. Sorry, C and D, my apologies. C and D. J crosses A and F, so minus AF. Again, K crosses A and E, and B and D. Remember to always subtract between the two vectors. If you've done this properly, you won't actually touch the first row, or first column, or the last column. So let's practice this using some vectors. Before we do that, another formula to calculate the magnitude of the cross product between with an angle of theta between U and V can be calculated. U cross V is equal to the magnitude of U times the magnitude of V times sine of theta. Realize this only works out the magnitude. It doesn't actually work out the cross product, or the size. It just works out the size of it. Okay, so let's try this out. So we're going to find out a vector that is orthogonal to 2, 3, 4, and 5, negative 7, and negative 9. So I'm going to work out U cross V. May I suggest you write out the values off to the side so that I, J, K, remember to write them in the same order. Okay, so we're going to work this out. We have 3 times negative 9. I'm going to write that 3 times negative 9. Subtract. Next time we have 4 times negative 7. That's our first component. Next, we have 4 times 5, minus, again, don't forget the minus, 2 times negative 9. Last but not least, 2 times negative 7. And then 3 times 5. And it's just a simple calculation. So negative 27 plus 28, 20 plus 18, negative 14 minus 15. So this is the vector 1, 38, and negative 29. So a vector that's orthogonal to both u and v is 1, 38, and negative 29. So we're going to confirm that this is definitely orthogonal to the vector u. You can do it also to v, but I'm just going to show you with u. So we're going to take 1, 38, and negative 29. We're going to dot it with our vector u, which is 2, 3, and a 4. If this turns out to be 0, then this works out. So 1 times 2 is 2, plus 38 times 3, that's 114. 29 times negative 4, negative 29 times 4, which is close to negative 30, so negative 120, but off by 4, so negative 116. So 2 plus 114 is 116, minus 116 is 0. And there we go, we've proven it. Since the dot product, since u dotted with u cross v equals 0, these vectors are orthogonal. Or again, perpendicular. Okay. So some properties of the cross product. If you work out u cross v, it's actually equal to the negative of v cross u. U cross v plus w does show a distributive property. Also, u plus v cross w shows also a distributive property. U cross v equals 0 if and only if there's a scalar value of m such that u is equal to mv. In other words, u and v are parallel to each other. And if you have some scalar m, u cross v with it, you can rearrange that m into any one of those vectors. Okay, so since the physical problems that deal with cross product deal with an orthogonal rotation, then the direction of rotation from u to v of the cross product relate to the rotation of the angle based on the right-handed system. So remember I mentioned that before this was the right-handed system that is being used. So if I'm going from u to v, this is my angle going in this direction. So u cross v would actually be going upwards. So you actually put your fingers, start with your fingers on u, then you curl your fingers towards v, and you stick your thumb out. So u onto v, sticks thumbs out, and then your thumb goes upwards. So u cross v would be going in that upwards direction. That upwards direction is a multiple of this vector, which they call the normal vector. And therefore, sometimes what they'll do is, if they don't actually know what the actual vector is of u cross v, but they only have the magnitudes of u and v, they'll do u cross v is equal to the magnitude of u times the magnitude of v sine theta, and they'll multiply it by the n vector. And this normal vector just turns out to be a unit vector. In the direction of u cross v. Okay. One possible application of the cross product is used in the area of a parallelogram. So as you can see, we have two vectors u and v that are tail to tail here, and they have an angle of theta in between them. Well, I'm not sure if you remember the area of a parallelogram, but the area of a parallelogram is based on base times height. On this case, the base just turns out to be the magnitude of v. The height in this case is the magnitude of u times sine theta. So you can see A is actually magnitude of u times the magnitude of v sine theta, which also turns out to be the magnitude of the cross product. And likewise, you can find the area of a triangle with vector v and vector u and angle theta in between, because it's half the size of a parallelogram. And thus concludes this lesson.